Hi S4, it's Mr. Bull here. Hope you had a great holiday weekend. We're going to be looking at energy again this week, but different forms of energy. So let's just get cracking with the first equation today. So put the title energy. And the first one we're going to be looking at is called kinetic energy. Now the word kinetic should ring bells from S1 science. And another word for kinetic is movement. So this energy that we're going to be looking at is movement energy, which relates to a whole bunch of stuff in the universe. So the equation for this looks like the following. EK equals a half mv squared. That's why we box around that. EK equals a half mv squared. Right, EK, as you might have suspected, is kinetic energy. So kinetic energy, that is measured in joules, as we found out from last week. We've got mass, which you will be aware of from other equations. And we've got V, which is velocity, which again you'll be aware of, and the units are meters per second. Right, so we've got kinetic energy, movement energy. We've got its mass and its velocity. We're going to explain that in 2 seconds. But first of all, let's just get our triangle so we know where everything comes if you want to use this for some help. So we've got EK at the top. Now we actually have to split this into 3. We've got half, we've got M, and we've got V squared. Now you can already look at this and be like, oh, it's going to be a little bit tricky if we have to find out, for example, V squared or V. But we're going to do some examples that will explain this and hopefully give you a little bit of help when you come across a question like that. Right, so we've got the equation, we've got all the units, we've got the triangle. Let's do a kind of everyday example of what would have a kinetic energy. So let's just take a wee road and a car. Okay, so here's my attempt to draw a car. Not bad actually. So that car, when it's moving, will have some sort of velocity V. And it also has some sort of mass of m, okay? Now, if it has a mass and it has some sort of velocity, then it is going to have a kinetic energy. And it's just as simple as that. Anything that moves will have kinetic energy. Wind turbines will have kinetic energy. That's how they create the energy. Even things like walking, you will have kinetic energy. Throwing something, it will have kinetic energy. So anything that moves and has a mass has kinetic energy. Right, so let's show you an example of Nova and I again with kinetic energy. Hi S4, I'm just going to show you kinetic energy in real life. We've got Nova, she's got some sort of mass, she's going to have some sort of speed, she's going to be producing a lot of kinetic energy with this throw. Okay, so take a look at this. Okay, Nova and I have hopefully helped you understand kinetic energy a little bit more in a real life situation, and we'll be looking at the worked examples very soon. But let's look at power now and the equation that corresponds to power. So let's write this down. It's P equals E over T. Now it's slightly different because we're showing it in this format. If we were to do the triangle for this, then you would actually see that E is at the top and P and T are at the bottom. Okay, please make sure you remember that. Lots of people get this formula wrong for some reason. So make sure that you know that E is at the top and P and T are at the bottom, and that will get it right every time. But what does this all mean? P is power. And power is measured in watts. All right, watts. So you may have heard of watts being used before in your house or whatever, but that is the measurement of power and the unit of power. E is energy. Now you'll notice that this one doesn't have P or K or W for all the energy we've looked at. That is because it is any form of energy that we're looking at in this case would just be normal energy, okay? And that's measured in joules. And then we've got T as in time, and that is seconds. So we've got power, energy, and time, and that is in the equation P equals E over T. Now, you may have seen this in electricity formats, how much wattage or the electricity wattage that you need to pay in your electricity bills for your mum and dad, but I'm going to show you a mechanical use of power in terms of cycling, because I quite enjoy cycling. So I'm going to show you another video, just very briefly, about watts and power in cycling. Hi S4, just wanted to chat to you about power, energy and time with regards to a bike. Now, when you look at power, you'll see that the equation, remember, is energy divided by time. So energy divided by time. Now, when you're cycling, you're going to be producing some sort of energy, or creating some sort of energy, and you're going to be putting that into the pedals. And that's actually work done because you're applying some sort of force to these pedals. And that energy will then transfer to kinetic energy because the wheel is obviously moving. Now you're going to be doing that over some sort of time. When you're in a cycle, you're going to be producing energy and you're going to be doing that over some sort of time. So in fact, you're actually creating power because energy divided by time is equivalent to power. So you're creating a power in watts. Now, you may have seen some things where you get a bike and it's powered to a light bulb, and if you cycle, you can power the light bulb. And it's actually true because you're creating some sort of power that actually causes things to work. Now, when you're in a Tour de France, if you were to ever watch it, these cyclists actually create about 200 to 300 watts in one stage. Now, that is enough to power your whole house if you wanted to in that time. That's a lot of energy, that's a lot of power that they're producing. Now, if you ever wanted to do it yourself, you could just buy one of these wee smart meters that record your watts from your bike. But when you're cycling, the energy you put in divided by the time creates some sort of power. And that can actually be a really good measure of how fast you're going, how good you are, how efficient you're cycling, and all of these things. So, power in cycling is something that the professionals use all the time, but it's something that hopefully helps you understand power a little bit more. Right, now that we've seen the two equations and some examples in real life situations, let's look at the worked examples and how to answer some questions on this. So the first two we're going to do is kinetic energy, so let's get stuck in with that. So for the first one, it says, what is the kinetic energy of a 3 kilogram trolley moving at 0.8 meters per second? So we know that it's kinetic energy, so I'm just going to write that equation down. EK equals a half mv squared. Now, a half, the mass was 3, and then it said times 0.8 squared. I'm just putting in what's in the question into my equation. I'm going to do that in the calculator. I just get 0.96 joules, which is our answer. So the first one's nice and straightforward. For the second one, number 2, it says a car of mass 1,200 kilograms has 614 kilojoules of kinetic energy. What speed is it travelling at? So already this one's a little bit more tricky. So I'm going to need to find out the velocity. So I'm going to do my triangle. EK is at the top, half m v squared. So we've seen that before. So if I was wanting to have v, I'm going to cover up my v squared. And you'll see that EK is at the top divided by a half m. So v squared equals EK divided by a half m. Now I want to get this v by itself. I don't want to have this square here. That's not going to give me my final answer. So there's two ways to do it. One way is just to find the answer for this first and then find the square root. Because remember, to get rid of a square here, you're going to need to find the square root. Or you can just do it before you put the numbers in. I'm going to do it before I put the numbers in. So square root of EK over a half m. Now, that's me ready to do my equation and find the answer. So the kinetic energy was 614 kilojoules. Now remember, kilojoules is not what we want it in, we want it in joules. So we know that kilo means times 10 to the power of 3, and that will give us 614 times 10 to the power of 3. The mass is in kilograms, that's fine, that's exactly what we want it in, so that's just going to be a half, 1,200. Okay? Now we put that in the calculator, and hopefully you know how to do that. You actually get rounded 32 meters per second, which is a reasonable answer. If we were getting something really small or really big for something that is a moving object like a car, that's not going to be right. But 32 meters per second seems about right for this one. Okay, hopefully that makes sense. Repeat it if you need to look at it again, and let's look at the next example now. Okay, so we have now looked at kinetic energy examples. Let's now look at power worked examples. So the question says this: a 5 kilogram box is raised through 12 meters in 4 seconds. So A asks, calculate the gain in gravitational potential energy of the box. So we're actually going to have to jump back to last week to get our energy so that we can then do our power equation. So let's just do EP equals mgh. That should be fairly familiar from last week. So remember, the mass in the question was 5. Gravity, remember, is 9.8, same as always for Earth. And the height is 12 meters. So that answer, 5 times 9.8 times 12, gives you 588 joules. And that's the potential energy of the box. Now, for B, it asks, calculate the power used to lift the box. So now we know the equation, P equals E divided by T. So E is just the energy we found out. Okay, so we know that it's not got a P here, but we know that we just found out an energy, and we need an energy, so it's just going to be the same as before. So 588 divided by 4 seconds, which is from the question. So once we do that, we get a power of 147 watts. 147 watts. All right. Just putting the numbers in, using it from our energy before, and we get 147 watts. Now, the last bit in this question says explain why more power would be needed than the value calculated in B. Well, because we don't live in an ideal world, energy is going to be lost to its surroundings in some way, shape, or form. So therefore, we're going to need to actually put more power in to overcome these forces, like friction, for example. Okay, so how would we write that? We would say something like this. More power is needed because energy can be lost to its surroundings. And you could even add due to external forces such as friction. Okay, so you'd actually need to put more power to overcome things like friction. Okay, so that's a question on power with a key of that equation there. S4, that's this week's work. Hopefully the work examples have helped. Try the questions, see how you get on, and we'll come back again next week for some more. See you later, S4.